Okay, intermolecular forces or IMF. Um, Anything with oxygen in it is polar. And there are two ways oxygen can be utilized. One is with hydrogen, and that's the strongest. Whenever you have OH, that is involving hydrogen bonding. OC is it's called a dipole dipole. It's strong, but not as strong as hydrogen bonding. Now we're going to see when we get into unit 3, we're going to have a carbonyl and an OH, which is even stronger than just OH. So whenever you think of OH now, that automatically reminds you of alcohols. OC is ethers, and this is acids because it's got dipole, dipole plus H bonding. We haven't got to that yet. That's unit 3. Um, so Connor, I forgot your question. It was regarding the ethanol, was it?
Just in general. Oh, right. The question on the study guide was why does ethanol undergo hydrogen bonding?
Yeah, so ethanol, it's got an OH in it. So all alcohols, uh, including carbohydrates now. I'm going to see in unit 2, glucose has got a whole bunch of OHs on it. Fructose, a whole bunch of OHs. So it's got a lot of hydrogen bonding going on. Um, Another question could be why doesn't diethyl ether undergo hydrogen bonding? There's no OH. Now, hydrogen bonding, think of NOF, NOF. When it bonds to nitrogen, oxygen, or fluorine, now fluorine's not in the body, so we don't talk about fluorine. Nitrogen, we're going to get to in unit 4, so it's going to undergo hydrogen bonding. And then the OH is, we're going to hit that in unit 2 and unit 3 and unit 1. Now, all molecules have something called London dispersion forces, or LDF. And that's all molecules. And that has to do with electrons. Like if we're looking at lithium, lithium has 3 electrons. And those electrons, 99.9% of the time, are not perfectly centered. They're off to one side or the other. Hence, forms a weak dipole. So it's weakly polar. So if I was to list the LDFs of any molecule, right off the bat, you list London dispersion forces, or LDF. All molecules have it. Alkanes have it. That's why they only have LDF. That's why they are um, weakly polar. Alcohols have it as well, but the hydrogen bonding is so much stronger, it overwhelms the LDF. You still have to list it though. So when you have a list of chemicals, say you've got alcohols, ethers, alkanes. These are increasing polar strength. Therefore, boiling point, melting point, and surface tension also goes up. So in the mix here, in Unit 1, we've talked about alcohols, ethers, alkenes, and alkanes. Alkanes are on the bottom. Alkenes are very close, though. They may be slightly more polar, very slightly more, though. Ethers, because of the oxygen in the ethers, definitely has some polarity. And the reason why alcohols are polar is because if you look at the electron distribution around alcohol, we've got these two unbonded pairs. And when anything bonds to oxygen, it ends up having a 105-degree angle. Therefore, it's lopsided and not symmetrical, and that's what makes it polar. Okay. So do you guys have any questions about intermolecular forces?
A lot of
What?
that made sense to me.
You're broken up, Connor. I think it was Connor who was talking.
Yeah, sorry. We're using Ryan's computer. A lot of that made sense. I think on the study guide, there were specific molecules that had different IMFs, and just going generally by how they were listed with the list that you gave, I think we got it. But I think it's just recognizing kind of which is which. Because I think, not yesterday, on Monday, I asked about ranking the molecules from like low to high boiling points and about the intermolecular forces.
Yeah.
And like the graph that we got in alcohols showed that like you could switch a couple of them around. I think the examples were dipropyl ether, 2-hexene, hexane, and 1-hexanol. And I remember you saying like the 2-hexene and a hexane were like kind of interchangeable. Like one might be more, one might be less.
Yeah, the alkanes and the alkenes, yeah. Okay, so if you look at molar mass, remember this graph? The alcohols were up here, then the ethers, then the alkenes, and alkanes. So as molar mass increases, their boiling points increase just because there's more mass to get into vapor. But in terms of we just chose 1 molar mass, we'd see that the alcohol version of that particular molar mass is more polar than the ether version, than the alkene and the alkanes. Connor, this was that graph you're referring to, right?
Yeah, that's the one.
Yeah, and see that follows this list here. So if you just remember this list, these have got oxygen in them. These have no oxygen. As soon as you add in that oxygen, it automatically adds polarity. And when you throw a hydrogen next to the oxygen, it intensifies that polarity. Now there's a chart of electronegativity. I don't know if you were given that in 305, but if we look at the periodic table, fluorine has got the highest electronegativity. Francium down here has the lowest. So they actually have a value. For example, fluorine has a value of 4.0. So when you look at, when I teach more detail about IMFs, you can actually look at the definition of polarity. What is polar? Okay, it has to do with the change of electronegativity is greater than 0.5. So if you're looking at fluorine and hydrogen's over here with like 0.4, so 4 minus 0.4 is 3.6, so it's much higher than 0.5. So an HF bond is very polar. But if you just remember, throw in oxygen for now, for unit 1 and unit 2 and unit 3. As soon as you start throwing oxygen in there, because oxygen's right over here, right next to fluorine. So it has very high electronegativity as well. It's like 3.6 or something like that. So did you go over this concept in 305? The difference in electronegativity and how that defines polarity?
Yeah, we did.
Okay, good. Okay, so anything else?
Professor, can we go over reactions that include heat?
Okay. Okay, if something goes from unstable to stable, it gives off heat. For example, combustion. We burn gasoline, and what happens? It forms carbon dioxide and water and a lot of heat. However, if we're going this way, we have to supply heat to get there to the unstable. So if we look at, let me grab the flow chart. Okay, so all of these reactions produce heat. Now, if you look at this one here, notice we go from an alcohol down to an ether or to an alkene. We have to supply heat. That means the alcohol is more stable than either the ether or the alkene from which it was derived. Okay, so for example, here, if we have to supply heat, like this one here, up here and going from an alkane to an haloalkane, we have to supply energy along with the halogen. That means the alkane is more stable than the haloalkene or the chlorinated alkane. These are plus heat. So we have the alkane with a spark, combustion, it forms carbon dioxide and water plus heat. And again, if we want to create the alkane from carbon dioxide and water, we have to supply heat. So your question regarding heat, I'm not sure that's kind of a general statement there, and I covered it in a general way. Do you want more detail than that?
Yes, I was looking at like from our dry lab that we did. It was like on the last page, those type of reactions.
The last page.
Like adding the H2SO4.
Yeah, so down here you're talking about, right?
Yes.
Okay. So um whenever we have an alkene, alkenes are unstable. So they want to become more stable. One way to do it is to add water, an acidic water. So what happens is the water adds across this double bond. No heat is required because the alcohol is more stable than the alkene from which we start. However, if we want to create an alkene, we have to start with an alcohol and we have to add heat. So when we have an alcohol, like this, for example, um, and we add some acid and some heat. If we add that much heat, what's going to happen is that's enough heat to go that's enough heat to create an unstable alkene. Is what happens is let's change that to one higher one, 180. Okay, 180 is very hot. Okay, and that tells you that this must be super stable compared to the alkene created. So what happens is we pull this water off right here. Now, sometimes you get a mix because if the OH is in the middle of the molecule, you've got an H on either side that can form water. So that's why you end up with a mix. Okay, so in this case, there's only one carbon adjacent to the COH that has an H. That's why we only have one product. If we had this, we would have H there and an H there. Hence, we would have one water here. So we would form this. And we would have one water over here to form an alkene there. The question is which is more stable? So we have Markovnikov considerations, symmetry. Okay, this is more symmetrical, and it's got more terminal hydrogens. So this is going to be the more stable one. Now, if we do this at a lower temperature, what's going to happen? It's not enough energy to pull off water. What happens is two of these link up together and form an ether. So I'm going to have two of these. And form an ether. So that would be dibutyl ether. And this would be butanol. Now the ethers, of all the reactions in Unit 1, this is probably the trickiest one up here when you end up creating a mix. On my flowchart I mentioned, I said expect a mix. Not all the time, but when the OH is in the middle of the molecule, you'll always get a mix. Okay, so did that help? Who asked me about the heat question?
It was me.
So Helen, did that make sense?
Um, yes, for the rule that was applied, yeah. I think I just would practice it more.
Okay, I'm not sure I followed you on that. Say again.
I just need to practice it more on my own.
Oh, okay, yeah. We have, regarding today's start time at 2, I'll be there at 2. If you have some reason where you have to be there at 3, like one person mentioned employment, I understand that you can start it at 3, that's fine. So if you want to start it early, you can start it at 2. I'll be there. I guess that's the way I should have worded it. I didn't mean to require everyone there at 2. Now, doing the dry lab is a good way to practice for this test. The dry lab doesn't talk about intermolecular forces, but it talks a lot about naming, going from name to structure, structure to name, and then reactions.
Professor, I put some reactions on the chat. Can you explain those to me?
Explain the what?
I uploaded some pictures of the reactions to the chat. Can you like walk me through those?
Let me look at it. Okay, we've got a so you've got an alcohol. Secondary alcohol. Now this thing can undergo a reaction at 140. And at 140, we're going to form an ether. So that means the OHs are going to be the connecting point. So we're going to have that. So that would be a dicyclohexyl ether. At 180, then we're going to start pulling off water. So here is an H here, and here's an H here. So that's going to be one double bond created. And then we have an H here. That'd be the other double bond. So that's going to be cyclohexene. This would be cyclohexanol. Now, are these different molecules? These guys here? So they are the same molecule. We just twist one or the other, we can create the other molecule. So in this case, there's no mix. If there was a methyl group somewhere over here, for example, there, you would then create different molecules. But with no methyl group, just plain old OH on that ring, you'd end up with cyclohexene with no other molecule. Okay, if we look at continuing on with this here, if we oxidized it, this is a secondary alcohol. Secondary alcohols oxidize to a ketone. So those are the three reactions with that molecule. Did that answer your question?
Yes, because I had done the one with the oxygen and I got that correct, but I was just stumped on the one with the 140, with the heat,
Yeah.
because I didn't know if I had to double the same or just add the double bond like I did for just the oxygen. But thank you.
Yeah, and with ethers, you need two of them. Now, all reactions in Unit 1, except for ethers, the backbone is the same. Start with 6 carbons, you end with 6 carbons. Start with 3 carbons, you end with 3 carbons, except ethers, because those are doubles. So if you start with 6 carbons, you're going to end up with 12 carbons. Start with 3 carbons, you're going to end up with 6 carbons. That's the only one that's like that. Now we're going to see in Unit 2, it gets more complex than that. But right now, start with 6, you end with 6. Start with 3, you end with 3. Okay, so let's see. Miranda, it says, is that only for ethers? That's the backbone doubling. Is that what you were referring to? With ethers, if you start with 3, except for ethers, you're going to end with 3. So for example, we look at we have 1, 2, 3, 4, and end up with 4 backbone as well. Say we're oxidizing there. You end up with an aldehyde. 4 carbons, 4 carbons. And then that's going to go to a 4 carbon acid. So ethers, though, because we have to start with 2 alcohols, that's why the backbone gets doubled. Better? Okay, you guys, good questions. Let's keep it up.
Professor, I don't know if I just missed this or I'm just having like the classification part of it, like as primary, secondary, or tertiary. Um, can you explain maybe a problem on that, please?
Yeah. Okay, so a primary alcohol is on the end. Secondary alcohols are in the middle. And tertiary alcohols are in the middle. Okay, if it's on the end, that means there are two hydrogens here. If it's in the middle, there is one hydrogen. If it's tertiary, there are no hydrogens. Okay, so you say, so what? To oxidize an alcohol, it's required to reduce the number of hydrogens or the number of electrons. And in OChem, we talk about reducing the number of hydrogens. In inorganic, like 305, we talk about reducing the number of electrons. So that means if we have two hydrogens attached to that carbon with the OH on it, that means it can be oxidized twice. A secondary cannot be oxidized once. And secondary and tertiary has no hydrogens there, so can't be oxidized at all. That's why it's important to understand what kind of alcohol you're talking about. Now we're going to see in Unit 4, it's going to be the same with nitrogens. Primary, secondary, tertiary. So is that help?
Yes, would it be this, let's say, it can it be at the beginning versus the end or no?
Yeah, because it's on the end.
So one octanol would be primary.
Yes.
Thank you.
Yeah. Or at the end. Because at the end, it's got, instead of linking up to carbon, it's linking up to hydrogens. And then when it's in the middle, doesn't matter where in the middle, but as long as it's not on the end, it only has one hydrogen because it's hooking up with another carbon, which takes up the other bond. And here we've got tertiary, we've got all carbon, carbon here, carbon, 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 all carbon bonds, no hydrogen bonds. So no hydrogens means it can't be oxidized. That make more sense?
Yes, thank you so much. And you did say that we're not going very high up, like only up to like maybe octa, right? That we wouldn't do like very high numbers.
Not for Unit 1.
Okay, thank you for explaining it.
Yeah, Unit 3, we're going to go much higher. I'm going to go up to like 24.
10?
But that's Unit 4. Or Unit 3. Okay, these are all real good questions. Do you guys routinely check your announcements and email? I usually, if there's a change in something, I usually put it out as an email and an announcement. But
I
if you don't,
tend to always, I get like notifications personally, but sometimes they are delayed. Like when you send an email, it won't go right away because it has to go to my secondary account because the school email is not my primary. So I kind of link it, but I do eventually get the messages, but not like so fast.
yeah. Well, same with me. When you guys send me a message, it has to go through Outlook. So I don't get it until it's moved over through Outlook. Because I don't, Outlook sends me all my messages on my phone. But messengers, uh, if it's only on Canvas, I don't see it. My Canvas is weird. I can only have one school Canvas on my phone at a time. Right now I have Sac City. So if someone sends me from Sierra, if someone sends me a message from Sierra, I only see it in Outlook. Now on my phone, I've got Outlook for both schools, but Canvas messaging I only see from Sac City. It's a pain to have that set up. They just I can't have more than one Outlook or more than one Canvas on my phone. So, and of course I carry on my phone 24/7. So that's my first kind of um, um, indicator if I have a message is through Outlook. Okay, we've covered the hard stuff, which was reactions, and we've gone through um, pretty much. I believe we covered pretty much all the reaction types. And don't forget when you do a reaction, make sure you make sure you name everything. So for example, on this reaction here, name the reactants, name the products, conditions to get full credit. Now, the only thing you don't have to name are aldehydes and ketones and acids. You just have to say ketone. That's unit 2 stuff. And acids are unit 3 stuff. They're not hard to name. It's another functional group you haven't covered yet.
Professor, are you going to be a stickler on like when we're writing down like 1 dash pentane 2 comma 3 dimethyl type, or
Stickler in what regard?
like in just in our when we're writing down, when we're actually naming the the structure, like if they have like methyl branches, are you gonna do we need to like write 1 comma 2 and then the dash ethyl?
Oh, I'm going to be a stickler if the problem is on naming. If the problem is a reaction, I'm not going to be as much of a stickler.
Okay.
But if I'm asking you to name something, then the naming is the whole focus. So now commas versus dashes, not so much. See, the main reason I stress naming is so you look at the structure. If you weren't naming, you wouldn't pay attention too much to the structure. This way, you focus on the structure itself, because the structure is where the chemistry is, not the name. Looks like we might get some thunderstorms tomorrow and Friday, up from a hurricane down in the Caribbean, not on the Pacific side of Baja area. So Southern California for sure, but they're projecting we might get some as well. So it should be an interesting day tomorrow, later in the day tomorrow afternoon, and then into Friday. Okay, so if there are any more questions, I'm going to give you guys some more time to study. And I will see you all at either 2 or 3. And you'll have, it doesn't matter when you come, you'll have the same amount of time. So if you come at 3, you'll still get, hour and a half. If you need it, even 2 hours. That's okay.
Thank you,
All right.
Professor. See you then.
Plus, I had a question.
Yeah.
I was wondering if we could go over the 1-hexene plus H2O.
Okay. That's going to be
The Marx rule, I think.
yeah. That's going to be okay, so here 1-hexene. So that water now is going to go across or add on either side of the double bond. 50% of the time, the OH is going to be on the right, 50% is going to be on the left. So we're going to end up with a mix. And then this one's going to be more stable. Because it's got one more terminal hydrogen, and it's more, they're both not symmetrical, but the one on the left is very, very lopsided. So Markovnikov and symmetry wise, the one on the right is favored. I think this was in relation to a Markovnikov question. Didn't I say explain in terms of Markovnikov?
Yeah.
Yeah. So you just say this has 5 terminal hydrogens. This has 6 terminal hydrogens. So 6 is favored over 5. That makes sense?
Mm, Where would we count the terminal hydrogens?
Huh?
Where would we count the terminal hydrogens?
How do you count them?
Or where?
Yeah, terminal means the end.
Oh,
So
okay.
end here, you count those.
Okay.
Now, if there was a, say, a methyl group there, you count those too.
Oh, okay. Thank you.
At the end, at the ends, if there are two ends, you count them. If there are four ends, you have to count all four ends. Does that make sense?
Yes, thank you.
Okay, so let's go ahead and end this, and I will see you guys, two of you that are left, in a little while.
Thank
Take-
you.
You're welcome. Take care now.
See ya.